distinguished invited keynote speaker to the stage to make his presentation. It's great honor for us to see Professor Siddique here and accepting our invitation. Let me briefly introduce some brief things for the Rafat. Siddique is professor, sponsored many projects and research at Tapa Institute Engineering and Technology. He has extensive teaching and research experience over 3 years. He is among top 15 academicians. Total citation of 18,000 plus, with having H index 72. Have 200 plus Q1 journal papers and 80 over the conference paper. Thank you, Professor.
Thank you, Victor, and very good afternoon. And it's a very challenging job to speak after lunch and more challenging for the audience so that they do not see it, So thank you, the Chamber of Civil Engineers, and for inviting me here. It's an honor for me. This is my first visit to North Cyprus. I have been visited almost most of the Western European countries, and I would give a special thanks to the chairman of the session, who basically got me connected to the Chamber of Civil Engineers. So you deserve more credit and equal credit to the Chamber of Civil Engineers. So. See, this topic is very vast, and if you really need to cover all this topic, you need at least 1 year of lecturing, 2 semester course minimum. So what my presentation is going to be technical, and as well as I would like to give some message basically. Otherwise, what we are talking about. I'll go through my presentation, but I will make a background first, and then we will go through some slides. If you look at the amount of whether it's waste generation or municipal solid waste or industrial, huge billions and billions of tons are being produced every year. And the percentage utilization is not that sufficient what we should aim for. So when we think from the civil engineering perspective, some of these materials have applications in structural engineering or in the sense of structural materials. Some have application in geotechnical engineering, but only their usage in civil engineering is not going to be solved with their 100% utilization. But as a civil engineers, we cannot take the onus of entire, like all the utilization as such. The focus is going to be how do we do it, and in some of the materials we have very established research, and for some the research is continuing, and for some the research is yet to be done. Not this is no. Maybe I think some problem with the connections. Can somebody help me? I'm not getting the first slide here. Okay. So I come from, like, say, it took me almost 24 hours, I must say, to reach here. This is like 330 kilometers from Delhi. So, and Professor Siddique has given me my background, so I'm still going to skip some slides. So let us come to the first slide. We have 3 types of solid waste. Solid waste from home office, industrial solid waste, we have from mines, agriculture, industry, and so the solid waste management basically, when we talk of this research, You can, for the people who are in the academics, they can publish in the healthcare construction building materials, they can publish in the waste management and resource conservation and recycling. So look at the waste generation. Say in 2020, for example, 2.24 billion tons total, out of which industrial solid waste like 6.7 billion tons, C&D over 10 billion tons. Even these are some of the figures which are not really accurate, because some of the countries really do not know how much C&D waste is. And agriculture waste over 6 billion tons. So, to summarize, what are the major industrial solid waste byproducts? And I'm going to focus on some of them. We have thermal power plants, all of you know coal ash, coal bottom ash, etc. And then you have certain things. So the disposal of these byproducts is becoming a very, very challenging. Maybe for a country like India, with a huge land, may not be landfilling, may not be issue, but in countries like, say, most of the countries, smaller countries in Europe or in, say, North Cyprus, you have a limited land. So you cannot even think of using land for refilling purposes. You must try to find out a solution so that you can use it. So, lack of land space, increasing cost of land filling. I do not know what is the cost of land filling in North Cyprus or Cyprus in US used to be, 10 years back used to be like $25 per kilometer. So there's a huge cost even for disposing it off. So I consider the utilization of industrial as an attractive alternative to disposal. So we want to, first of all, we want to reduce. So we use a lot of plastic bottles, waste glass. So reduce, reuse, recycle. That is number one best option. Second, waste prevention. And third, burying, burning, and shipping. Like you must have heard the news. Some of these waste from Australia comes and dumps on the ports of China and India countries. Okay. So, the problem is these are some of the listing of the byproducts you have. I'm not going to speak it. Out of this, some have established research. You know what are the final conclusions. For some, the research is still going on, and for some, the research is still to take place to reach to solid conclusions. For example, waste glass. For example, I'm going to cover some of them. The problem which bothers a full-scale utilization of waste glass is its ASR, alkali silicon reactions. Once we are able to fully solve it, we have solutions. Once we are able to fully solve it, this is going to be a wonderful material, either a cement replacement or a sand replacement, etc. So some of them, and out of these, I'm going to cover 2-3 to give you some of the scientific results, and then send a message. What is going to be there? And before I do here, most of the byproducts I am going to cover are going as a replacement of fine aggregate. My research is spread all over use of any materials as a replacement of cement, fine aggregate, but for the last 10-15 years, the major focus has been on the utilization of byproducts as a sand replacement. The reason is why, my argument is, we can produce cement, but we cannot generate or produce fine aggregates. So, and most of these industrial byproducts, some of them are listed, can be very effectively used as a fine aggregate replacement. So I'm going to cover 3 here. One is going to be coal bottom ash, the other is going to be foundry sand, and the third is going to be waste glass. And maybe all of you are aware of the research, but I want to give you some idea about what I'm going to talk about it. Say you made a control concrete or the reference concrete, say 50 megapascal, for example. Some concrete you made. Then we made certain replacement, foundry sand, coal bottom ash, etc. And the value of the compressive strength has come down to say 25 megapascal. We as a civil engineer, I do not know the mindset of the people in the North Cyprus, but generally, see, compressive strength is one of the most important from which we define the concrete basically. So people say the strength has decreased by 30%, 40% or increased by this much percentage. So we always talk in terms of percentage. And even if I say some strength has decreased, has come down to 10 megapascal, 15 megapascal or 20 megapascal, that still is useful. The reason is we have a misconception that when we talk of concrete, our mindset only goes to a structural concrete. The concrete which you are going to use in the high-rise building, structural concrete. Like in India, we use minimum 20 megapascal concrete. I don't know what is in Cyprus, function maybe minimum 20 or 25 megapascal. But the concrete which you use for making paving blocks, stones, like when you walk to the say, restaurant, you have paving blocks. That doesn't require 20 megapascal or 25 megapascal or 15 megapascal. Even by utilizing such materials, even if the concrete strength is low, and we are able to 10-15%, 10-15 megapascal strength, we are able to utilize the byproducts. The focus is you should not worry about how much reduction. The focus is where we can use that concrete. So let me I think it doesn't like my presentation something. Okay. It's not working. So this will give you some idea of how much waste is generated. And percentage utilization is, some of the data is available, some is not, but it gives you like how much scrap, tire, coal combustion byproducts is all generated. And this presentation is with the organizers, those who are interested, and if they allow it, you can always have it. So, how do I do? There was an economist, Adam Smith, he said, every process is immortal. It never loses its entirety. And this kind of research, we are also talking of kind of a circular economy. Even if the glass bottle is you have thrown it, it's again going to be used. So kind of a circular economy basically. So these are 3-4 benefits. Environmental benefits you have if you use these byproducts, economic benefit, and the product benefit. Economic benefit, you save the cost of fine aggregate cement depending upon what you use. So these 3 I am going to cover, and if the chairman gives me a few more extra minutes, so I will be grateful. So this coal combustion, we have 3: fly ash, bottom ash, and boiler slag. I am not going to talk about fly ash because every literature is there that maybe thousands of papers. They are going to talk about coal bottom ash. This is the fly ash generation. Look at the in India, 197 million tons, 120 million tons. So this is the situation. So actually, the problem with the coal bottom ash is why did I choose this? It is hollow inside particles and it reduces the workability. So not many people wanted to use it, but as I said, if this much quantity, I will show you this table. Look at it. By 2030, it is going to be 600 million tons only produced in India, fly ash. If you assume 20%, I'm talking from Indian perspective, and then you can go for a global perspective. Coal bottom ash is generally around 50 to 20%. So 120 million tons of this is going to be used. So it's difficult to use in concrete. So you need to design a concrete mix. So we have 2 options basically. The point which I want to convey a message as such. If you simply say it's difficult to use in the concrete, so run away from here. it lie like this, let it spoil the environment, let it spoil the land, water table, etc. Or work hard to find out its solutions. So this is my approach for any of the byproducts. It may be harder, but the time has come, we all must focus on finding out from the civil engineering point of view, the possible uses. We cannot use all, but we can certainly, and I will show you some results to justify it. I'll come to the, directly this is the table you have, like water absorption, calcium oxide values are very erratic because it depends, you're talking of class C fly ash or class F source or class C source, a lot of variations. The particle size are crystalline in nature, they are porous, so many people do not try to use it. We started this research almost 8-9 years back, and through one of the PhD students. So these are the irregular particles, so your workability also gets affected. So people don't want to touch it as such. But my thing is, any material, you must find out the solution. May not be a structural concrete, maybe on lean concrete or a low-grade concrete. Okay, let me come to this. Say, for example, this slum. I told my student, replace all up to 100% finally. Let us see what happens. It's an unknown territory. And this what is to be done for any material to be used. Look, see, slum goes down, you know. So remember this slide. When we talk of concrete research, basically, let me put it this way, we should not judge the suitability of concrete only by one of the properties. One of the properties means I'm talking of fresh properties, strength properties, and durability properties. We need to take into account in totality all the three parameters. Because I'm going to show you a slide of compressive strength. If you only look at the compressive, this is Siddique. Okay, this is another, he's a professor in England, some of you must be knowing, very famous researcher. And here you'll find very contrasting research results in coal bottom ash. Because particle is porous, particle is crystalline, hollow, so what type of particle size you have used. But generally the workability is going to decrease. This is a result I am purposely showing you that you may also get some type of other results. So generally workability is going to. Now look at this compressive strength. Don't forget the slump. Look at this compressive strength. Look at the 28 days strength. Look at this graph. You will feel on the cloud 9, top of the world. He said, even with 100% I am getting how much? Even with 28 days strength, I am getting around 35 megapascals. Even with 100% replacement. Any field engineers will say, wow, nice, 35 I am getting it. But for a structural concrete, you also need to have workability. Please remember, you also need to have work. This is the point I am trying to highlight. You need to see three properties in together. You only look at this is misleading. You need to see, then you have to see what slump, which percentage gives you a workable slump. You're looking for a structural concrete to pick up that percentage. Similarly, some of the various other people are trying to find out, and you will see the compressive strength more or less the same, doesn't because you're using superplasticization for compaction or compacting, so you're getting the compressive strength. Look at this, almost similar things. This huge number of papers are just trying to put certain papers just to give you a message or idea. Similarly, strict tensile strength, one slide I put it. Seeing the first author is one of my PhD students, and similarly, flexible strength, almost same trend, not much of decrease. I'm coming to the permeability test. Look at this. This all falls under your at most at 28 moderate category or low category. So you need to see three: workability, if you're talking of structural concrete, then workability, and then your compressive strength part. See, resistance to sulfate attack. See, after our research, we were the kind of first in coal bottom ash and foundries and in the world to use in the concrete. Many people have started, even in Turkey and all over Europe. See this, even shrinkage resistance sulfate attack is very, very effective. See, basically, let me put it in general thing. When we try to use these byproducts in concrete, my point is, even if it doesn't increase any of the parameters, keeps the concrete at the same level, or even if little bit 5% decrease, still I will have to use it. Because the kind of money you save as a cost of price of cement and price of fine aggregate. Second, the amount of money you save in line filling costs. And more important, there is no measurement of the amount of money you save from saving the environment. So even if but most of these byproducts, they do improve the durability. They do improve the compressive strength. So that is a win-win situation. This is a very common question anywhere. What happens if it reduces by 10% or keeps the same level? Even then, we must use it because you are saving otherwise the cost. So these are some of the things. Sign again. Not working. Oh yeah. See this again. The Fourier envelope. See, I'll give this credit to him. 99. He is a professor in Illinois Institute of Technology. He was the kind of first person who published paper on coal bottom mass. But seeing the issues with the workability, he left the research. Then I said, we started it so that we need to find out solutions. See, dry shrinkage, all within the STM range, STM parameters. So it is not, none of the properties getting adversely affected. Point of the message. Abrasion resistance, and you can use in the road construction, subway, waste courts, etc. kind of thing. So the conclusion, if you look at it, and if you're looking for a structural concrete, I would say 15, 20, 25% is very, very safe because it gives you decent workability and good durability. But if you're looking for a higher percentage use, which you can use in paving blocks, paving stones, or hollow blocks, we can go for a larger replacement as we do not need very good workable concrete. Second is, this is the waste boundary sign. This is a research we started globally in my school. And after that, you'll find a number of papers floating around. And then I gave these two names, which is very popular in the elsewhere, the spent boundary sign and the waste boundary sign. What is this waste boundary sign basically? This metal casting industry, I'm sure there must be many in North Cyprus and Turkey also. It is made of a silica sand. And the molds are made of silica sand, then you add certain chemicals to make the mold. And then the molds are heated up to say high temperature. And once it is heated many times to make the molds, the sand loses its cohesiveness. And once it loses its cohesiveness, it becomes useless for the industry and they throw it out. And once they throw it out, I first used the name waste boundary sand. But then I started hating the word waste. Something which you are using it, you should not call it a waste. So I gave the other name, a spent boundary sand. A spent the sand which is already exhausted its utility in the boundary. So these two names we kind of gave it. So look at the physical, they are angular. So when we started this, we found the properties are similar to fine aggregates. And sand, natural sand is a huge issue in India. I do not know what is the issue in Turkey or other parts of the Europe, but that is a big challenge. As I said, cement you can manufacture, sand you cannot manufacture. So look at this part. These are chemical composition, is very rich in silica. And these are the likely applications. If you put in the Google say boundary sand, you will find I would say lacks of article on use of foundry sand on CLSM. People in the geotechnical engineering may be knowing it. It's called controlled low strength material, which is called it flowable fill. But for the concrete, we started the fundamental research here. So I'll show you some of the results of our things. Look at this graph. Look at this graph. For a person who wants to criticize, see, very small increase or decrease in the bar chart. That can be part of a statistical error. Yes or no? Maybe 5% increase, 5% decrease, part of a experimental error. Somebody wants to criticize any research, which people do, why you're wasting your time in this subject. Look at critically the graph. If even with the 25% waste boundary sand, our strength is not decreasing. This is the point I want to highlight. Even at 20% is more than the control. And since the particles are fine, they behave like particle packing behavior. So that is the reason you get the things. After my research was published, a very good friend of mine, who was professor in Wolverhampton, UK, Jamal Khatib, I think these days he lives in Lebanon. Then he called me, he said, I want to replace up to 100%. I said, well, go ahead. Look at this. It's Khatib, 2013-14, we worked simultaneously. Look at this graph. Even 60%, you are getting around 25 megapascal. So there are two perspectives to look at this graph. One is, you can, if you are very bent on criticizing something, you can say that strength is decreasing like a hell, you know, useless research. But if you want to find out positives out of it, even with 60% replacement, you are getting around 25 megapascal. Even with 100% replacement, you are getting a strength which is more than enough for a pavement blocks, paving stones, etc. So the idea is how you are looking at it and what is the purpose. Our purpose is, at least my purpose is, to find out solutions to use in certain construction materials so that we do not have issues like landfilling, etc. etc. Because concrete doesn't mean only structural concrete. Concrete means like right from 10 megapascals to 200 megapascals. So depending upon things, we try to find out. See, similarly, I think he is an author from Turkey. I don't know which university. I see. Look at almost same thing. Similar. The split I am skipping because split I will skip again. Elastic modulus. Look at the rapid chloride permeability test. It is behaving. It has improved the durability also, permeability also. So here this is a win-win situation. By using up to 20% or 25% things, we are improving the strength, improving the durability. Because only with the compressive strength you cannot judge the concrete is good or concrete is bad. You need to see the durability. That is very, very important. This dicing salt also doing very good results if you have a look. Ultrasonic pulse velocity also gives you indirectly how the concrete microstructure is, how it is behaving. It has gone into all, as per a code, it is considered as a good quality concrete. Abrasion resistance on like 15-20%. We can see this is also produced in huge quantity globally on this side. And this I can tell with more authority and confidence. Then this is a better material than coal bottom ash for use in the concrete. Because this is not a hollow material, this is a solid material. And very similar to your natural sand or river sand. What do you call it in North Cyprus? River sand, natural sand, or fine degree, whatever you call it. I have not included, but I will give you an idea. Those who may be interested, they can contact me. After this, when you start a decision, we just at some point of time you come to a stage, you just don't believe in publishing. If you talk in Europe, particularly Germany and the US, I'm not about sure about Turkey and not Cyprus. Whenever you want to justify to their agencies in Germany or France, they want to find out what is the leachate analysis, how it is going to affect the soil. If you're using, say, MSWS or foundry sand or coal ash or any material. So they want to do the leachate analysis. We have done it, not included in the part, in association with a professor in microbiology in my school. And we have done treated foundry sand with microbes, fungus, bacteria to improve the leachate quality. As such, this material is not dangerous. You do not need to do those researches. It's a very, very safe material as such. But if you do like you go for the use of hospital waste tests, for example, or municipal solid waste tests, in that, if you really want to publish papers in good journals, you must include this. Otherwise, everybody does fresh properties, everybody does strength properties, everybody does durability properties. So what is new in your research? So if you do this leachate part, your publication will have a better value. So similar to the conclusions here, easily you can use 15 to 30% in structural concrete and property. You want to use higher than that, Jamal Khatib reference is more than enough. Now coming to this waste glass, again you know how much is generated. Just have a look at this. Different types of glasses you have. Okay, and this quantity increasing exponentially every day or every year. And we simply cannot say we have an ASR problem. ASR problem is solved to a large extent with the use of metacholine and silica film, etc. But see, look at the quantity. Worldwide is how much? 113 million metric tons. Like India, that much. Whatever data I could get. But this is huge. Look at that. Recycling, nothing. And that usage we have to find, and this can be a wonderful material, I'm telling you, for cement replacement and as a fine aggregate replacement. But with a caution, you need to be careful in grinding to the proper size. If it is irregular size, instead of helping it, maybe you may not achieve good strength for a structural concrete. Otherwise, lower grade concrete, there is no problem. So this is how it particle shape, particle size for the benefit of the audience. You know, high in silica, but it has all calcium oxide, silica oxide, ferric oxide. So to be very honest, if you once it is finally fully solved ASR problem, it could be a wonderful material to be used in along with silica film and fly ash for high performance concrete, because it has decent amount of the calcium oxide, aluminum oxide, etc. So these are uses of waste glass. And look at how the I think the first author is from Turkey, is very how does the unit weight varies, air content? There's a very marginal change in the air content. The graph looks like, when if you look at the axis rating, very marginal. But again, again, not from the Bible taken, that this is the only research available for the unit weight. There's a lot, but it gives you an idea of how to go about it. Slump, look at the slump, not a problem. 20% replacement, decrease in percent. So this is not a substantial decrease. To be very frank, I'm not concerned if property decreases. I'm not concerned as a civil engineer as a concrete materials. I will use in the other type of concrete. Objective is to find out its usage basically. Look at this. I think his first author is from Canada, McGill University. See, there was early research in 2000, late 90s and 2004. But because of ASR issue, So people dropped it out because you cannot use in the durability part. But now the solution is coming up with the help of supplementary cementing materials. I'll show you some graph here. Serial compressive strength. Look at this. Even with 100% replacement, you are getting how much? Around 65 megapascal. But again, this research alone can be misleading. You need to see durability properties and particularly ASR along with the workability. But this, look at this. Came at all. Similarly, split tensile strength results more or less similar. And come flexural. See, if you look at some of these flexural strength, the good strength achievement is consistent, is not much decreased with the control. Any whether research in Korea, research in Turkey, or research in Canada, something. So compressive strength is not an issue with this material. Water absorption, look, even it decreases, which is good in a way, but not to plus replacement. Is Song et al. From Korea, Lee from Korea. Silica reaction. This is the thing. If you find out this solution and we have a solution, then this is a wonderful material for concrete standard finite layer cement, whatever you want to use. Look at this. Relative extension. These are the things that general. See here, look at this. The permissible is a 0.1, and then for 100%, you got this scheme at all. See this. This is a solution with supplementary cementing material. Look at this graph. Without fly ash, you have the high shrinkage. With fly ash, all within the range. Similarly, if you use fly ash or silica fume or metacoline or rice husk ash, you can control the alkali aggregate expansion, alkali silica ash. And anyway, if you once we design, let me go to the other one. So look at this. This is with metacoline. Look at this graph, metacoline. The latest research published in 2020. Look at this. With only 5% metacoline, all concretes, right from 0% glass to 50% glass are almost within the range of 0.1% expansion. And anyway, when we talk of high performance concrete design, whatever my knowledge goes, you cannot produce high performance without supplementary cementing materials. It can be, and not only one, it has to be in combination. Silica fume alone is not sufficient, it has to be GGBS or rice husk ash and metacoline. So even this glass can be a wonderful material once you are able to, and the result shows, look at the other result also. Same, it is below the things. Similarly, these are the green brown glass. So thank you, and with this I wanted to basically the 2-3 points which I am repeating it again is finding out the solution. And if you are the one who is starting, I remember when I first took the research on West Boundary Sand, I used to get jokes from my own school, are you going to make it, are you going to mix the chicken curry something with it? So when you do something new, there's going to be resistance. People are not going to accept it easily, let me tell you. But once it is accepted, I am giving you some secrets of publication. Once it is accepted, your paper is going to be cited very, very well. because you are going to be like first in the things. Like most of papers published in foundry sand have my references. Initially, there was a lot of resistance. What is this material all about? Say glass also. Similarly, the waste plastic, because in 40-45 minutes, I said cannot make it. But again, the next important topic is waste plastic, scrap tire. The only issue comes up with the for structural concrete is the bond between the concrete and the plastic. We have some solution, but it's not that we can blindly use in the structural concrete. So, and we have to find out a solution if we want to save our environment, landfilling, and reduce the cost of your concrete. Thank you. I think I take that much time.
No, it's okay. Thank you so much. I think that's.
Any questions? No.
Let us take some question and then. Any question?
There is one.
Good afternoon, sir. Thank you very much for the presentation. My name is John from Cyprus National University, Department of Civil Engineering. So my question is, some of these waste materials, and I know most of them, they require additional processing that might also add in energy consumption. So how do we reconcile the issue of the energy consumption to save the environment for environmental impact assessment?
Excellent question, and the answer is very simple. The material which I have, the first two at least, the first two I presented, coal bottom ash or foundry sand, they do not require any processing. They do not require any processing. Obviously, if you bring foundry sand from industry, you need to sieve it through, 4.75, sieve. You need to remove some boulders or particles. Otherwise, technical processing is not required. And let me tell you, if you are going for a certain processes which is energy intensive, it's going to increase your cost. And you really do not know whether the use of such material is really going to give you a structural concrete or not. So you need to really find out whether we need processing or not. This like glass doesn't need it, You need to have only a very fine crushing machine. Uniform particles gives you. As such, there is no other treatment needed. You can do your research. Research is a different ballgame. I am talking from a very practical usage. If you want to use foundry sand by treating it or by coal bottom ash or waste glass, by treating it, processing it is going to increase your cost by 10%, 20%. As a common man, I am not going to buy that concrete. Even I am not going to buy it. Why? I say he has used some materials which I am not aware of, and he is asking for 20% more cost. So the idea behind this research is you should, like in typical some material, imagine some material which is not available in North Cyprus. And you want to bring it from, say, Istanbul. It is going to give you a huge cost increase, I believe. So it's not, you're not bringing 1 cubic meter, you need thousands of cubic meter of things here. So concrete research, ideally, unless you're going for a 200 megapascal concrete, that is different thing. For normal concrete construction, try to use your local available material. Trying to import something, the cost is going to increase. Similarly, if you need processing for what? If you take a material, do the physical test, chemical test. Obviously, I'm not saying you don't do any test. Even in your laboratory, if somebody comes with a bag of cement, you perform certain tests before use. Yes or no? You perform certain tests before use. So do the same testing for this also. Because material research should never use even cement without testing, like consistency, setting time, etc. So, in my opinion, processing, at least for these materials, is not required. Because I want to use it, not necessarily in a structural concrete. If it fits in, Wonderful. Doesn't fit in, there's so many other scope for using in the component. I hope I am able to convince little bit to you.
Any other question?
Hocam, you can use this. Hocam.
Yes, sir.
Thank you very much for this nice presentation and inspiring presentation for us. Just a quick question. In this respect now, when we do this kind of research, there are mechanical improvements. Also, we have environmental aspects. These are the pillars under the sustainability, actually. Also, we have the cost, and on the other hand, we have the social. Can you give us some hints regarding the social aspects of this kind of study? Because this is which we are currently seeking to answer in that sense. So, when it's mechanical, compressive strength, durability, these are the things. When it goes to costs, it's economical costs we can calculate and see the differences. And environmental, life cycle assessment can be done. But in the social part, can you give us some hints regarding the social impacts of these replacement materials?
I really could not understand what exactly will be the social aspects.
I mean, how would this affects the social side of the communities who use those?
I can answer to very lighter side. Say, I'm walking on a road, for example, on every side you have waste plastic 9 or waste glass 9. If it's clean, you definitely would like better, I'm not doing any studies on the social side. But the other point which you raised, life cycle assessment, that can be a good, I not done it because at this point of time, but that can be a good thing to take up. That could be a good point to take up, life cycle assessment. That can be good, some of people can take up. But see, those things, social aspect, what this is a good point, life cycle assessment. See, when you talk of any research, you got some material from, say, give me tomorrow, right? Not that you straight will jump to durability properties. It's a step-by-step process. First of all, you have to see whether it's suitable or not. You do not need to close your eyes and start using it. You have to find out its physical, chemical, morphological, and properties, and then see whether it's suitable or not. First of all, you need to judge its suitability from ACM standard or Turkish standard from the cement perspective of fine grit property. Find out their physical properties. Then try to use in the cement, few tests to it. Once you keep encouraging it, then try to go for it. And not see, please do not misunderstand me. I want to use these materials blindly in concrete. No. They need to satisfy, like concrete center, for example. The finest models is similar to fine aggregate. Their particle shape is similar to fine aggregate. I omitted one chapter here, wood ash, for example. I spoke in Bursa a few years back. We tested wood ash from at least 100 sources. And then when we did the physical chemical analysis, then we only choose those which fitted into ASTM C666, sorry, ASTM, what is the code for polyolefin material? It's skipping my mind. So you need to do that space, not saying blindly go for it. There are some other, even like in fly ash, for example, it has more better application in agriculture engineering than in civil engineering, fly ash. So you need to do all check whether they can be done or not. Like glass, for example, want to use a cement replacement. There's a good silica oxide, good calcium oxide, good aluminum oxide. So these things gives you confidence. Its properties are similar to cement, so we can use particle size, so we can use a cement replacement. So those things I'm not saying you just skip it. No.
Thank you so much. Any question? Okay.
Laboratory testing of viable soils to present a token of appreciation to our keynote speaker, Professor Dr. Rafat.